into the diesel cycle. No, not Vin Diesel, but the diesel cycle, which came from Rudolf Diesel. The diesel cycle is the ideal cycle for compression ignition engines. The combustion process in these engines take place over a longer interval. So due to this longer duration, the combustion process in the ideal diesel cycle is approximated as a constant pressure heat addition process. And this is the only process where the Otto or the diesel cycles differ. In a gasoline engine, there is a spark plug that ignites an air-fuel mixture. In a diesel engine, you have a fuel injector that injects fuel, and what happens is when the compression causes the temperature to reach an ignition temperature, then the fuel air mixture combusts. So that's the one difference between it. One is a spark plug, one is combustion by compression. Here are the processes that make up the diesel cycle. You have process 1 to 2, which is the compression cycle. Again, this is the same as the Otto, more or less similar to the Otto. We'll put similar instead of the same. So it'll be similar to the Otto cycle. This one is different than the Otto cycle, the next process, which is the constant pressure heat addition process. In the Otto cycle, it is a constant volume process. Process 3 to 4 is also similar to the Otto cycle, which is isentropic expansion. And then process 4 to 1, which is also similar to the Otto cycle, is constant volume heat rejection. So we have process 1 to 2, isentropic compression, 2 to 3, constant pressure heat addition, 3 to 4, isentropic expansion, 4 to 1, constant volume heat rejection. So the diesel cycle occurs in a closed system. But let's go ahead and analyze what's happening during the Q-in process, right? The constant pressure Q-in process. If you recall, from the Otto cycle, the Q-in process was equated to the difference in internal energy, right? Because it is a constant volume process. Well, if you do a first law for the diesel cycle, in the diesel cycle, you have Q in, and you also have work out because it's a constant pressure process, not a constant volume process, equals delta U. So actually, if you carry out the first law, equating that the boundary work is at constant pressure, which ends up being pressure times change in volume, you end up with Q in as delta H, or with constant specific heats, Cp delta T. And process 4 to 1 is the same as it is in the Otto cycle, which is a constant volume process. So a first law would be delta U, or if you the Q out would be delta U, or if you were to approximate using very constant specific heats, it would be Cv delta T. The efficiency, I left the equation on the slide instead of writing it in. The efficiency of a diesel cycle is quantified the same way as it would be for any other heat engine. It is net work over Q in, where if you were to substitute Q in with the first law analysis on the cycle, Q in minus Q out, you end up with 1 minus Q out over Q in. Now with the Otto cycle, actually you could substitute Q out and Q in with Cv delta T, right? And the Cv's cancel out, but not for the diesel cycle. The diesel cycle, the Q out is constant volume, the Q in is constant pressure. So you have Cv delta T for Q out and Cp delta T for Q in. And if you recall, K, which is the specific heat ratio, is Cp over Cv. So you make the substitutions into, if you go ahead and substitute K as Cp over V, you actually can replace Cv over Cp with 1 over K, and you end up with this correlation that I just circled as the thermal efficiency for the diesel cycle. Now, there's a few other terms that we need to familiar ourselves with concerning the diesel cycle. One is going to be something called the cutoff ratio. We're going to define the cutoff ratio as the ratio of the cylinder volumes after and before the combustion process, right? So if you go back, the combustion process is Q in, and it's going to be the volume ratio during the combustion process, right? Namely, it's going to be nu3 over nu2. So again, the ratio of the volumes before to after the combustion. I'm sorry, not the combustion. The combustion process, the Q in process. So again, that would be the cutoff ratio. Utilizing that above definition and also combining it with the compression ratio. If you recall, there is a compression ratio for the Otto cycle. The diesel cycle also has a compression ratio. The compression ratio is nu1 over nu2. So you have two things. You have the compression ratio and the cutoff ratio. Okay, so those are two different ratios that are used for the diesel cycle. So if you were to go ahead, you can use those definitions to define the thermal efficiency of a diesel cycle as a function of the cutoff ratio, the compression ratio and the cutoff ratio. So the efficiency of a diesel cycle differs from that of an Otto cycle by the term in the brackets, which is always greater than 1. So the result indicates that the Otto cycle efficiency is greater than the diesel cycle efficiency. But as the cutoff ratio decreases, the efficiency decreases. So here you can see as an example of a graph, you have the diesel efficiency on the y-axis and the compression ratio on the x-axis, and several different lines showing the increase in the efficiency as a function of the compression ratio for different cutoff ratios. So as the limited case that the cutoff ratio is 1, the efficiency in the Otto and diesel cycles become identical. But the dependence on the thermal efficiency on the compression ratio R and the cutoff ratio RC is shown to the right. In practice, diesel engines can operate at much higher compression ratios than spark engines, and therefore oftentimes are much more efficient than spark ignition engines.